I really appreciate your attendance at my presentation, and this is the topic of my presentation. My name is Farhad Eliasi. I'm a master's student at University of Utah in EC department. And this is my presentation outline. Firstly, I'm going to define my problem, and after that, I will introduce my proposed model. And finally, I will show you simulation results. The stability of power system has been recognized as a major challenge in maintaining the security of the system. Extensive research has shown that many blackouts that occurred in power networks are initiated from power system instabilities. Frequency stability is the ability of power system to maintain its steady state frequency in case of occurrence of a severe disturbance in the network and resulting imbalance between generation and consumption value. So when the load of the network is more than its generation value, the phenomenon of frequency drop appears in the system. So if this frequency drop is severe, the generation's speed or frequency is decreased to supply additional electric power. And after that, with continuation of the frequency drop, power plant units would be out of the circuit due to the operation of the frequency relays. And after that, with the intensification of the power mismatch and further reduction of the system frequency, it may lead to a cascading and regional blackouts. So when such instabilities happen in the network, since the past, load shedding in the system has been proposed as a way to preserve network frequency stability. In most of the conventional schemes, the settings of the UFLS relays is usually based on an operator's experience and network behavior in various events. In the last few decades, many studies have done to optimize the setting of UFLS relays. But there are some factors in the recent schemes. So the lack of the optimal method to adjust the relay parameters have been highlighted in this research orientations. And the other one was that they didn't actually consider incident severity in the model. And the last one was they consider the frequency the only parameter in decision making. So in this study, we need to address all of those problems, and we need to minimize the amount of load shedding and increase safety. So, an IEEE model based on a row curve as a measurement of the magnitude of the event is introduced in this study. So now in this slide, we are gonna actually define our proposed model. So we know that the frequency behaves almost the same throughout the network. A multi-mission system is usually modeled as the multi-mission system is usually modeled as a single mission system, whose oscillation equation you can see here in this equation. So in this equation, the delta G is the amount of the generation outage, the delta D is the total amount of load shedding, and the last term is the impact of the load damping factor. And the H is the inertia of the system. So once the frequency oscillation equation is known, this equation should be converted to a discrete time form. In order to discretize it, we need to consider this formula, and after the discretization process and using the Euler method, our new B function or swing equation can be calculated by this formula. Actually, I'm going to say that to set the frequency load removal relays, two variables are decisive. And you can see here the delta DS, the amount of the load at each step, and the frequency of each step. And also, to evaluate the performance of the proposed method, we need to define appropriate scenarios for understudied network. So we need to define some scenarios. Sorry. But in the next step, I'm going to show you how trip command activates in UFLS relays. Actually, in the event of the generation outage, the frequency begins to decrease. when the frequency of the system passes the fs value, then a binary variable v should be equal to 1. Otherwise, it should be equal to 0. And next, when the v is equal to 1, next, a counter should be activated. If the timer measured by this counter exceeds the delay time value, delta d, a new binary variable u should be equal to 1. And this and the trip command u is sent to the circuit breaker, and the load with the amount of delta d should be shed. You can see here the process. But in this model, we need to add a Rokov to our model. So in the proposed method, the amount of the load interrupted in the first step is a function of the frequency and the rate of the change of frequency, the Rokov. So in the next step, I'm going to show you how the trip command activates in the first step, which is combining of the Rokov and the frequency. Actually, the binary variable W is used to model the possibility of the load shedding based on a rate of change of frequency. If the magnitude of the frequency change rate, which is equal to B, you can see here, is greater than the assumed threshold value RL, the value of the binary variable is equal to 1, otherwise it should be equal to 0. But as I mentioned before, the load in the first step is shed only when both indices, Rokov and F, exceed their threshold values. So we should check for the AND logic of the two binary variables W and U. We need to model this with this formula. We need to define actually a Z new variable Z. So if the Z is equal to 1, the trip command for the first step should be sent to the circuit breaker. And it should also be mentioned here that if the binary variable Z is equal to 1, this value must retain until the last, must remain 1 until the last time sample. To satisfy this condition, the binary variable Y should be defined and two constraints should be added to this constraint. So after actually defining all of those variables, new variables, the B should be formulated by taking into account the frequency-based term and the Rokov-based term. And as you can see in the new B equation, the F-based and the Rokov-based terms are not linear. So we need to linearize those terms. How we can linearize those nonlinear terms? Actually, we can actually by adding these two simple constraints, and these two constraints for the U times by delta D, we can linearize those two terms and we can define our new B like this one. So the new B is totally linear. So in the next slide, I'm going to say that we need to add some constraint to have a precise mathematical model. In fact, it is impossible to recover the removed load during the load shedding process. So we need to add this constraint. And also the load should not be shed in different steps at the same time. So we need to add this constraint too. And in the proposed model, there must be a priority for the order of removing the load. The smaller the index S, the higher the priority for the load shedding. So we need to add this constraint too. And finally, we need to define a stopping criteria for load shedding scheme. So we need to add this constraint to stop our load shedding scheme. So I'm going to show you actually our objective function. The main purpose of the objective function is to minimize the amount of load shed for all scenarios and in all steps. Actually, you can see the objective function here and the PJ. In fact, the PJ is the weighting factor for each scenario, which is calculated by the frequency of the scenario occurrence. So in the next slide, I'm going to show you my simulation result. Actually, two case studies have been conducted to evaluate the performance of the proposed model. And actually, in these studies, the system is assumed to be a single bus. And for the case one, I consider RL, or the threshold value for the Rokov, is equal to -0.8. And after solving the problem, all of the settings are obtained. You can see here the first step, delta DS is equal to 0, because actually, in fact, the W and the Z, which is the indicator of the frequency load shedding at the first step, is equal to 0. That means the load shedding value in the first step should be to 0. So the load shedding process to recover the frequency starts from the second step. So the load shedding in the second step has the greatest effect on the objective function here. This is actually the frequency drop figure in each of the scenario by applying those settings. You can see here. And for the next case study, actually, I changed the RL value to -0.2, and all of the settings are obtained. And you can see the delta DS for the first step is changed. And you can see all of the figures for frequency drop here. That's it. And in total, I think it was observed that by using the Rokov as a criteria for the load removal, in the first step, the total load shedding amount is reduced and the security of the load removal plan is still maintained. And that was it. And thanks for attending this presentation, and feel free to ask any question.